Mhm. Hi, Maddie.
Hi.
There, 14, 15. There we go. Yes, I need that one open. Yeah. I'm getting it. I'm coming. There we go. Bing. 2, 3, 4. All right. How we doing, kids?
Good.
Good. Andreas, wake up.
Where'd he go? He left. Good job, Smap.
You're not going to make me feel bad about yelling at you to wake up in my class. I'm sorry. But if you come in and you go, and your eyes are closed, no.
Just saying.
I thought
What do
my sound was gonna break again like it did 2 weeks ago, so I tried to join again. In
I
the
mean,
earlier Zoom, it like didn't
I'm
work.
just saying, you guys have like 2 hours of school every day.
False.
You have an hour of school.
No, I wake up at 6:45 in the morning and work till 1.
Do that.
That's
Dude,
smart.
when'd you
I
leave?
don't know how I woke up for school like before. Now I wake up at like 8:30.
Carter, where you going? Carter, where are you going?
The airport.
Are we going somewhere or picking someone up?
There's my mom.
Hi, Mom.
I'm taking her to the airport. Because I have to drive the car
Technically,
back.
she's taking you to the airport.
Yeah, I was about to say the same
Yeah.
thing.
If
Yeah.
you don't have the steering wheel, buddy, you ain't taking anybody anywhere.
We're going to New York.
Yeah.
Woohoo! Ding, ding. 12 is a good start. There we go. Ola Bobella. Fourteen's good. Not great, but good. Bobby, can you see without your glasses? Okay.
Yeah, I can.
Okay. I was a little worried there for a minute. Madison, what you got?
While we're waiting, can I ask you a homework question or should I wait?
Is it an easy homework question?
To me, no. To other people, maybe.
Sure, give it a shot.
You know the on like the first worksheet, the really like long, complicated ones, like number 3, or at least in my opinion, like I'm not really sure where to start, like what to start with. Like what to start doing.
It's a KEQ worksheet, right?
Mm-hmm. But
Okay,
this one
now hang
asks for
on.
like the moles at equilibrium, and then it's like a 5-part or like a 3-part thing.
Give me a 3-part thing.
Like there's a part A, a part B, and a part C.
Yeah, but they're all just asking concentrations, aren't they?
No, the first one says what is the number of moles of them at equilibrium.
Okay.
And then the second one says what are the other one is concentration, and then the other one is KQ, but I don't know how to do the first one.
Okay, so let me fly through. I got 4 examples, but I can get done with those in about 20 minutes, and that'll give us 10 minutes to take a look at that question at the end. So you
Okay.
get first question up when I'm there. And we're close enough because we're still missing people, but it's 11:08. We got to go. So kids, here's what we got. Okay, so before I hop into KEQs, this one was a 3-part chapter. All right. Part 1 was rates. Those were the charts. This one doubled, it's first order. And we did that. And those worksheets seemed to go pretty well last week. I looked at those. So now we've got to do the second one, and that's equilibrium. And this one is the hard one. Then the third one is thermo. That one's very easy. That one is just plug them in and get the answers. Plug and chug. Not hard at all. Okay, so if we look at our ammonia reaction, let's say, before I even get into the KEQ, if I was to grab N2 plus 3H2 and we got 2 ammonias made, suppose that we had half a mole of N2, then theoretically, just using stoichiometry, just using the ratios, wouldn't it make sense that I'm going to need 1.5 of this, and I'm going to end up making 1.0 of that? Now those numbers just came, if there's a 1 in front of the N, then 3 times 1, 3 times 0.5 would be 1.5. And there's a 2 in front of this, so 2 times 0.5 would be the 1.0. So Madison, this is kind of the how many moles? This is the how many moles question. All right, but to do these equilibrium problems, we have to put them into concentration. So we would then divide all of these by whatever volume flask it was in. Divide by your volume. I didn't specify here. But all we're really saying is in proportion to moles, that if this were X, this would be 3X, and that would be 2X. And if the reaction was going forward from left to right, we'd be making 2X, so that would be positive. We'd be using up or consuming the nitrogen and the hydrogen, so that'd be negative, and that'd be negative. Those would get consumed.
Can I ask a question now?
Sure. Okay.
So like what if there was like no 3 or 2 in front of the H2? What if it was just like a coefficient of 1, 1, and 1? Would it just be like
0.5, 0.5, 0.5.
Okay.
Everybody would get the same all the way across. Great
On the
question.
worksheet, it does not work out like that. Like on the calculator, like if you like calculate it, like it does not work out like the way that you're explaining.
You're right. Because all I'm doing is, yeah, I haven't given you the answer to the worksheet yet. This is just saying how many moles could you get? And then you got to go back.
Yeah, but for the ones on the worksheet that says how many moles do you get, like if you multiply it out, like it does not work.
Well, did you take into account the K value yet?
Yeah, I can just ask during office hours. That's fine.
Okay. Yeah, because let me get through the examples and I'll be happy to get to the homework. All right. So now we've got two types of problems coming up before we get to the worksheet one. The first one is given concentration. So these are going to be, get a label in there, Steve. These are going to be from concentration. We're going to calc KEQ. That's what the first two are going to be. And then the second two are going to be given KEQ, go back and get the concentration. All right. And once again, don't copy this stuff, guys. I'm doing it for you. I will get done with my AP class after this one, and I will post this afternoon, early this afternoon. This will be on the weekly module underneath Tuesday. You guys found it last week, right? I'll post it up for you. So now we've got a 1 liter flask. We've got a half a mole of nitrogen, a half a mole of oxygen, and 0.02 moles of nitrous oxide. This is 1 liter. So the first thing we do is take all those and find out, calculate the molarity. Just divide them all by 1 liter. Now I got the molarity. Now the KEQ, if it asks for the equilibrium expression, they're asking for the symbolic products to their exponent, to their coefficient, times the over the reactants to their coefficient. So this 2 coefficient in the equation became a 2 superscript. So now I take that NO 0.02, plug it in, square it. Then take the 0.50 and 0.50, plug those into the numerators. Algebra.
Smith,
And solve whatever you want to do to get the answer to that.
can
Right.
you say what the what KEQ equals again? Like how you know the NO2, whatever.
Yeah, sorry, that's a good point. Let's back up a little bit. This KEQ is called an equilibrium constant. Now, when we did rates, we had a little k that was cursive, and my cursive k's look kind of funny. This is a big capital K, and it's going to represent a ratio of products to their coefficient over reactants to their coefficient. And the higher the value of K, the better the reaction goes from reactant to product. The more the reaction proceeds as written from left to right. So that's the big picture of it, and that's what it is. That's a good point of backing up. So we take and put our product, our 0.20 squared over 0.50 times each other. We're just plugging in the concentrations, and we get a K value here, 0.10 to the negative third. It's a really small number. These K values can be very, very, very small, like 10 to the negative 50th small. And these K values could be as large as 10 to the 21st, 10 to the 22nd. They can be huge, they can be small. So don't say, well, I did a problem and I don't think I got the right answer, because it doesn't seem right. These values can be anywhere in the spectrum. There's no way for us to know if it's right. So let's look at another one where we just have to plug in concentrations and calc a K. So here's one where we've got a 1 to 1 to 1 to 1, 1 to 1 to 1 to 1 ratio. And they tell us that at equilibrium, the following amounts are found: 53, 53, and 47, 47. Okay. These happened in a 500 ml, a half a liter flask. Okay. So take the 53 over 0.5. Take the 047 over 5. Calculate those out. All I've done is set up products over reactants. Now I get a K that's a little bit closer to 1. If I get K equal to 1, what that's telling me is I'm going to have equal amounts of reactants and products going on. It's not necessarily all that golden, because we don't want equal amounts. We usually want the reaction to either go one direction or the other direction. We don't want it sitting in the middle. So those first two examples are, given my concentrations, just plug them in and calculate K. Now let's go backwards. So now we're calculating concentration from a K. You've been told here's the reaction, and the K is 5.6, and quite often it will say at 25 degrees Celsius, or it'll give you a temperature with the K. You guys don't have to do anything with that temperature. That temperature is being given in order to validate what the K value is, because the K is going to change with temperature. When you raise the temperature, usually you raise the equilibrium constant. So that's the only reason they give you the temperature, is to validate that number. So in this case, it tells us what it is, and it says, what's the equilibrium concentration of NO2 if in a 1 liter flask there's 0.66 moles of the product, N2O4, at equilibrium? Okay, so if it's 0.66 in 1 liter, then the N2O4 is 0.66. The equilibrium expression is simply products over reactants using their coefficients. That 2 coefficient became a 2 superscript, became an exponent. So we know the 0.66, we know the KEQ, we don't know the NO2. So at this point, plug this into NSolve and just use a variable down here that this is X squared. And NSolve that, and you'll get 0.34. That's my concentration. So now we're getting closer to what you guys are talking about on the homework problem. So let's look at the last example I've got, unless you guys get others. I'm open to questions right here before we do the last one. So now I've got bromine chloride. Whoa, don't go there. Bromine chloride. Going to decompose into Br2 and Cl2. This is a 1-to-1 ratio here. So a sample of BrCl is allowed to decompose in a 1 liter flask. At equilibrium, the mixture contains 4 moles of Cl2. So now we're in the moles. The first one, this one I think is real similar to what you were asking, Madison. So now what it needs to know is how many moles of Br2 are present. Well, if there's 4 moles of Cl2, that's going to equal 4 moles of BR2 because it's a 1-to-1 ratio. And then I got to divide those by 1 liter. So now I know each of the products, but what I don't know is the reactant. And so now I put 4.0 over the x squared and the 11.1 and end solve this. So just stick an x in your denominator, x squared in the denominator, and solve this for x. And you should get a BRCl of 1.2 molar. Let me play what if just for a sec. What if we had the BRCl and don't ask me, let's see. Suppose we did that. And now I've got a 3 here. If they told us this was 4.0 moles, how many moles of BR2 would there be? Anybody? Bueller? Come on, Al.
12.
12. 12 moles. Now that's in 1 liter. That's in 1 liter. So now we'd say 11.1 equals 12 cubed times 4 over x squared.
Wait, it's math. So
Yeah.
why is it an x squared if you know there's the 2 BR3CL?
How about that one? 2x squared. And this is, I think, what you were talking about, Santiago. I think. Okay. So I haven't solved this one yet. Let's see here. 4, 12.5. So now x is equal to 12.5. What's the concentration of the BR3CL? Anybody besides Bobby? I don't know. Did Bobby answer the last one? Who was that answered the last one?
8?
It's me.
8?
No, sorry, I'm just guessing.
25.
She's trying her best.
Thank you, Emily. I appreciate it.
How do you know, Emily? You don't know she's trying her best.
Well,
She's doing
I wouldn't
better
say
than
anything.
others. At least she said something.
At least I said something.
I could make a random guess.
Would it be
25?
25?
Yeah,
That's-
that's what I was gonna say.
Wait, why can't
Wait, but how do you know? I've lost.
If it worked perfectly, you would get 2x here.
Oh, that makes sense.
Oh, it does. It's hard. It's hard. I'm not fun in here. This is like the hardest calculation we do because this 2 coefficient gets used for an amount, 2 there, and an exponent, 2 there. Once for stoichiometry, and then once for equilibrium.
On the other one, didn't you have to also, but you didn't? Did you times it by 2 or no?
Yeah, I should have had a 2x in there.
Mhm. When you have to find like the concentration and then find the moles, did you already find the moles up there? with this?
So you mean now we know the concentration of the Br3Cl, but we want to know how many moles there are? Just multiply it by the volume. So if we
Oh, okay.
take, yeah, we would have 1 liter times 25 moles per liter. So we would have 25 moles. Whatever that volume is, multiply it by the volume in liters. Is this what you were talking about, Santiago?
I don't think so, but I understand that.
Okay, there's another one out there, but come to office hours, we'll chat.
Yeah, sure.
Because I don't want to open that. I know which one you're talking about, and I don't want to open that can of worms until people have had a chance to digest this. Madison, I said you were up first. Did this answer your homework number 3 question?
No, not really. I
Okay, so-
understand what you did,
Yeah.
but like for the example, they gave us 1 mole, like they gave us the mole on the reactant and the product side.
Okay, so read me the question so I can kind of get an idea what's going on here.
It says when 0.4 moles of PCl5 is heated in a 10-liter container, an equilibrium is established in which 0.25 moles of Cl2 is present. Yeah, and then they give us that. And then the Cl2 is 0.25.
Thank you. Okay, so initially we started out with 0.4 moles of PCl5. This is number 3?
Yes.
Okay. We started out with 0.4 moles of PCl5. And at equilibrium, we had 0.25. So,
Sorry, that was me.
ooh, that was loud. Okay, so if there's 0.25 moles of Cl2, there's 0.25 moles of PCl3. We're okay there, right? And then the PCl5 is going to be 0.4 It's going to be 0.15 moles of that present. This is the hard part, is where did that 0.25 moles come from? It came from this 0.4. This 0.4 broke apart and formed some PCl3 and some Cl2 in a 1-to-1 ratio. So how much of the PCl5 broke off? 0.25 of it. So there's 0.15 of it left. So that answered a couple of those first questions. And then the last one is probably what's the KEQ, right? So now you know it's these moles in a 10-liter container. And then just set it up. The KEQ is going to be PCl3 Cl2 PCl5, and that's going to be 0.025 0.025, 0.015, and that should give you a KEQ. That's a lot in not even a half hour. Get into this worksheet. The second one is long. The first one's okay. The second one is a little bit long. Or no, the first one is long. The second one is short. All right? If you have questions, pop into office hours tomorrow or let me know. And I can do some Zoom stuff tomorrow. I gotta go to the dentist in the morning, but I'll be back, and I can find some Zoom time with you. Okay, but give them a shot first. Who's got?
What kilo for the number 4? It has plus 22 kilocalories. How are we supposed to add that?
Kilocalories. Oh,
Yeah,
that's just a measure of heat.
Hmm.
And okay, what's the question asking?
What's the value of K at a temperature of 1000 degrees Kelvin if the following concentrations are present at that temperature?
And it says kilocalories?
Yeah, it like has plus 22 kilocalories.
What worksheet are you on, Ella?
Staff, it's the first worksheet, number 4, but I did it and it doesn't matter. Like the KCAL doesn't affect it. The
Yeah,
an-
it probably doesn't.
Okay, so we just don't do anything with it.
I'm opening it up right now. No, because what we're doing, KEQ and number 4
Yeah.
at a temperature. Oh, and no, it's just giving it to you.
Okay.
Yeah, you don't need to worry about that. That is going to come into play where you see energy. It'll come into play when you get down to number 13 and 14 and you're doing Le Chatelier and you're shifting equilibrium. So yesterday's video was the theory behind it. Today's video was the calculations behind it. And tomorrow's video is the Le Chatelier's principle behind it. Okay. Thermo 2 comes up. That's plug and chug. And that's real straightforward. We're looking at our next quiz a week from tomorrow. You guys asked for more worksheets with answers. So if you look in the practice area of this module, there is a rates worksheet or rates 2, a equilibrium 2, and a thermo 2, all of which have answers on them. So you wanted more practice with answers. There you go. Okay. Questions, problems, concerns? Email me if you got them. If not, come into office hours tomorrow. Okay. And we'll get you straightened out. But give these a shot. Don't procrastinate this one till Friday afternoon. You're not going to be very happy. Okay. It's a lot of work this week. Next week gets a little bit easier. Beamer, get here on time. Come on, dude. All right. We'll see you guys next week. Thank you.